So we want to be faster than this. So what do you have in mind? So the desired, we are looking for the desired eigenvalues of the observer error matrix, right? We want desired eigenvalues of the observer dynamics. So make a choice. Yeah, it should be on the left-hand side, so it should be a minus. Let's make it 2 times faster. Would that be good? Something like, approximately 2 times. Let's make it, 30. It's not exactly 2 times, but it's 30. That is, the closed loop was at minus 17. Right? The open loop you can find from here. What are the eigenvalues over here? I think one of them is in 0 and one of them was somewhere else. Right? So you want to take this. This is the open loop. The closed loop, the desired closed loop of the system should be here. So we designed a feedback controller such that the closed loop eigenvalues are here. So there's somewhere, it's like that. Real, imaginary. And the closed loop eigenvalues are at minus 17.7 and 17.6668. So they're here. Here it's the same. So these are the closed loop eigenvalues of the closed loop. They are desired, but when we design the feedback gains of the controller, this is where the closed loop will be at the end. Right? So, where should be the gains of the observer? I'm just saying, let's put it somewhere there, and maybe something like this. Minus 30, so let's make this one, hopefully this is here at minus 30. And maybe this one we want to put at plus minus 1. Well, let's do that too in a minute, okay? Because we want to move them. They're complex, so let's move them together. And let's see what happens, okay? Sorry. Plus minus 1j, okay? Desired eigenvalues of the observer aerodynamics. I moved them all over here. We want to have them here. I don't know what the feedback gain should be now, but I want the observer dynamics, the observer aerodynamics to be here. Observer aerodynamics. You understand what I'm trying to do, right? I see some empty looks sometimes and I'm getting scared. I'm not moving the open loop eigenvalues or the closed loop eigenvalues of my LTI system. I'm just trying to design an observer to estimate x2. In fact, there was a question during the break. Someone said, well, we are only measuring x1. What are you talking about? There's no x2 over here. Well, that's the whole point of observability. We are not measuring x2, but given the system, we can estimate x2. If the system is unobservable, then we can't estimate x2 at all, because we don't see it in the measurement. Here, x1 and x2 are connected to each other. So based on that connection, if we only measure x1, we can still estimate x2. That's what observability means. The fact that x2 is not measured here doesn't mean x2 is not observable. Do you understand that, right? It is just not measured. But we can estimate x2 based on that. And that's what we are trying to do. We are trying to estimate x2. So we already designed controllers. That's out of question. What we are doing now is, how do we estimate x2? How do we estimate x2? Well, we are estimating it through an observer. What I'm trying to do now is, what should be KE so that this should work? Okay? So when I say, let's move the observer aerodynamics over here, I mean this dynamics, the aerodynamics here, I'm sorry, here, the aerodynamics here, we're trying to move it to a point where x hat is approaching x in a certain speed. Okay? And for that dynamics, I would like to put the eigenvalues of the observer aerodynamics somewhere here. Okay? So if that's the case, can someone find the characteristic equation that corresponds to this eigenvalue? Can you do that? So it will be something like this. Lambda minus, let's do it like that. Plus j times lambda plus this is the characteristic equation, right? I just made up this number, so I don't have the solution. You have to help me with the calculations now. All right? So can you calculate this? You are like, what, 40 people? It will be lambda square times, please do it and someone tell me and help me. You're on camera. 40 people, Middle East Technical University. Give me the result. It will be on YouTube. Plus 60 lambda. Now we are getting excited. Huh? Plus or minus? Plus 901 equals 0. Is that right? Good. Okay. So that's that's the one. That's kind of funny. Okay, so this is what we want as a closed loop dynamics. So this is E dot is equal to A minus KE times C equals times E. We want the eigenvalues of this to match these eigenvalues and therefore this characteristic equation. So we're going to look at this one, of course. The determinant of lambda I minus A minus KE times C is equal to 0, right? And we want this equation to match that. So let's do this. It will be lambda square plus 3 plus KEI times lambda plus 8 times KE2 equals 0. So why did I do this? Let me write it down here maybe. I think I can maybe remove this part. Since we know the system is observable, right? Okay, how did I do this? Well, I did A minus 3800, right? Minus, so what should be KE? Should it be a vector or should it be a matrix? What should it be? It should be, I mean, we have C over there, so it's 1 and 0. So it should be right? this is what you get from here. Let me write this whole thing. Okay. Just going to write it. That is equal to then okay, A minus KE times C. And you realize that, you know, you have one output over here. So this will be 1 in this problem. It will be 1, 1, 1, right? And therefore you will have one number over here, right? That y. And you need to multiply it with 2 k's, but this should be a matrix here now, because you're adding it to x dot hat, right? So you're adding it here. So this should be a matrix over here, right? Because A is a matrix, so you're going to add the A matrix with this matrix, and it will be that. Okay. So anyway, this is that, this is this, and if you do that, this will become this. Okay? So, can you tell me KE1 from this? It's 57. Is that right? Yes. And KE2 will be equal to 112.624. So 100.2 point. So. Okay. So these are your feedback gains. So I guess I can just write it down on this, on my figure here, what the block diagram of the observer and the actual dynamics actually will look like. And 112.6. Actually, do it like this. This will not be a matrix. I apologize. This was just wrong here. You get I hat minus y from here. This will be your error y, right? This will be one number. You will multiply this number with these two numbers, and you will get a vector here. Sorry, okay, that was wrong. I mean, I got confused with the c times k, which is not really here. Of course, c times k is in the equation, but it's not here. Here you're multiplying ey with, I mean, the error here, you multiply with this vector, and then you get another vector over here, and then this is a vector. X times a is a vector, so that is a vector, that is a vector. You add them, take the integral, so the output here will be x dot hat, okay? So this is what your observer looks like. And from here, you will get x hat as an estimate, and you would send that estimate over here. And this will be now your controller that uses x hat. And theoretically, this x hat should be equal, right? Should be equal, or x hat should reach x as time goes by. Okay? Now, here's of course in practice. First of all, any questions on this whole thing? Yeah?
Do we have x2 inside of the x cap right now?
Yes. Let me write this nicely. X hat is x1 hat and x2 hat. Okay? Now, theoretically, x1 should match the measurement x1. I mean, according to this, we are measuring x1, right? Y is equal to x1. Right? Y is equal to 1, 0, x1, x2. So y is equal to x1. So we do measure x1, okay? Isn't it? I mean, in the problem, we are measuring x1. So therefore, actually, what comes out of here, this is x1. This is x1 hat, right? And then this is really x1 hat minus x1, right? So that is really the error here. So EY is really x1 hat minus x1. So using x1, I'm estimating x1 and x2. Now, of course, you might say, well, I'm measuring x1 already. Y is equal to x1. Why is y equal to x1? Because of this. Right? So why is it equal to x1? Okay? So you might say, well, we are measuring x1 already. Why are you using this x1 while we already have the real thing? Right? The answer is you can. Of course you can. Okay? You can use x1 from here, and you could use x2 from here. So in practice, I think this is what we do. This is what we would do anyway. Okay? We would use x1 from the real measurement, and x2 would be just what comes from the observer. Although the observer will give you x1 and x2. Okay? You could use that too. I mean, according to our calculations, without doing this, everything should still work. Okay? But I can't imagine anybody measuring a number and still using the one from the observer unless there's some other reason. Is that clear? So any questions on this? I encourage you to try this in MATLAB now. I mean, the last hour on Wednesday, if you haven't been in class, I did MATLAB Simulink examples on the controller designs. And you could actually try this now at home on Simulink. Okay? And see if you are getting actually the right x's from here. I mean, in Simulink, since you are already calculating x from here, right? You could actually compare this x with this x and see if they are actually matching. Okay? But make sure that you do change something in A and B or somewhere, or do a disturbance somewhere. Because otherwise, if you start everything with the same ABs, you won't see an error over here, because this and this is the same, right? So you will see 0 in the output. You need to do something or change something over here and see if you're still coming close to this estimation. Okay? This could be a nice homework, actually. Let me think of that. All right? So, you have any questions?
Can't you get rid of from imaginary parts?
Okay, want to try? Let's try. Let's say we don't want to have that, but we want this. So you want to have both on 30? Well, it will be difficult because then you will have y minus 30. Sorry, plus 30, right? Plus 30 equals 0. And what do you get from here? What do you get? Right? Is that right? And this should match. This should match this. Well, looks like you can. Okay. I would say so, but there might be cases where you might run into trouble. That's why I'm always scared not to do that. But here in this case, it's okay. Okay. Any other questions? Yeah.
How do we know our choice of eigenvalues are good enough?
Well, you don't. That's why we need engineers. If you ask the computer and it gives you a number, we don't need you. We can always ask because I tell you how to do it. You can program this into the computer, right? And I ask the computer what's the eigenvalue and it tells me and gives me the result. I don't need you anymore. The question here is, of course, you need to be faster than the closed loop. You can't be too fast. If it's too fast, then you might run into troubles over here. Note that you're multiplying these numbers with 100 to the factor of 100. So in fact, this 30 might still be too high, right? I don't know. I would ask you, how good is your measurement? That would be my question. Okay? But we know that this is going to converge faster than the closed loop. This is going to converge faster than the closed loop. So this is already something that we know at the end. If this is what's required for the closed loop, because the closed loop will be the requirement. If you have an airplane and there's a disturbance, the designer will tell you, you need to stabilize this aircraft in 5 seconds. That's the requirement. So you do this, 5 seconds, I want to be stabilized. So this will tell you what the requirement for the closed loop is. So that means your eigenvalue, the observer dynamics must stabilize itself, or the error must go to 0 before 5 seconds. If the aerodynamics goes to 0 in 10 seconds, then you will never achieve that 5 second requirement. And that's why we make it faster. Okay? What happens in between from 0 to 5 seconds, that depends, of course, where this one is. Because it will, if the error goes quickly to 0, then the oscillations will only, or whatever, the transient will only happen here. You know that, right? We call that transient. So let's say this is your x or your y, and this is time, right? And you want to go from here to here. Okay. This is what we call the steady state part. Right? And this is here the transient. Okay? And when I say eigenvalues are at a certain point, I always mean that, or, it stabilizes itself fast because the eigenvalues are large numbers. So that really means that it stabilizes itself fast, means that how fast do I come to this point? Right? That's all that matters. That's all I'm asking, really. How fast do I come to this point? The transient part, I don't talk too much. I mean, the complex part, of course, talks about the transient part, right? The transient part could look like this. And you could still come to the same steady state, right? So when I say the eigenvalues over here, they must be faster than the closed loop. All I mean is that if the closed loop needs to be at the steady state at this point in time, then the observer must come to a steady state faster than this time so that we actually can reach the steady state at this time. But depending on how you design your observer, depending on where you put this or where you put your complex eigenvalues, the transient might look different. Say the real response is the red one. I mean, the closed loop response is the red one if you measured everything. But since you don't measure everything, if your observer is perfect, so that it immediately catches the actual measurement, then the result will still look like this. But if your observer is bad, has a lot of oscillations, your transient will look like this. But you will still reach the steady state like we say, because the convergence is faster. I mean, the question of, that was a question in the last, what if we have larger complex values over here, right? What happens then? Well, what happens is that you will still be fast enough to reach the steady state in time. The problem is that the steady state will probably have oscillations too. Okay? So when I say faster or slower, I always mean faster convergence or slower convergence to the steady state. What happens in between is actually a different question, which this doesn't really tell you that much. It just tells you there will be some oscillation. But if the system becomes larger, there are interactions like an observer and a controller. What happens in between is really not very well established. Okay, does it make sense? But as I said, all these questions are the things that aerospace engineers have to deal with. Okay. For instance, in this case, let's say this measurement is the pitot tube measurement. So with the pitot tube measurement, U is measured, the pitot tube, right? With the U measurement, can you estimate Q and theta? Just looking at the pitot tube measurement. Well, theoretically, yes. These are, if they're observable, of course. If they're observable, just measuring the pitot tube, I could, and given the controls, I could estimate theta and Q. Will this happen in practice? Well, it's a question mark. Because the pitot tube measurement is never a very clean and nice measurement. Right? That's why the airplanes have a few pitot tubes just to take an average and all this. Okay? But again, these are the things that you have to... So if I tell you you have a pitot tube and you have a gyroscope, you measure Q. Can you measure theta and W? Now you're saying, yeah, I think so. Because now you have at least something that gives you the angle, and you have a velocity, and this represents the angle of attack, and this represents theta. So there is a chance that we might be able to estimate these things. Now you have a feeling for it, right? So where is that feeling coming from? If I would show this mathematically to somebody, they would say, of course, with a pitot tube you can measure everything, right? So you're laughing at that. So this is kind of why you need aerospace engineers doing the control systems. Understand? And your question, how do I know if this is good? Well, we really don't. And that's why we need you as an engineer. Is that okay? Okay, so there's one more small topic which I can probably do in 5 seconds. Not 5 seconds, 5 minutes. And then we can all go home. Observer and controller design. Observer and controller design. The question is, if I design an observer in this particular architecture, will the calculation of this k change? That is the question. I think we already have that feeling that the calculation of this k will not change as long as this is faster than this one, right? This is kind of the feeling we have hopefully now. I just want to show this to you in a somewhat different way. The designs of the controller and observer can be independent. Preferred to have observer error dynamics faster. So we had this, and we had this. Oh, let me do this, sorry. Okay, so I'm just writing this one here, this equation here. Okay, I think I never wrote this explicitly like this. And this u here is the one that comes from there, and that u is equal to r minus k times x. Okay, and now you have two equations like this, and E is somewhat related to that. So I can write this together. I can write this in the following form. In short, after a few manipulations, you will get E dot x is equal to okay, so what I have here now, you might wonder what I'm doing. I have now an LTI system that is kind of correlating both the aerodynamics, the aerodynamics and the estimate, but it is matching them with this A, B, K, the controller gain here, right? This is the controller gain, and you have this gain and that gain, and you have everything kind of together in one set. Okay, the error and the estimate of the real thing. So what we are going to look at is, if you would look at the transfer function of x hat s and r s, you would find something like this. Look like this. And this is the relation between x and r, the input. This is the input, and these are the states. And the transfer function looks something like this. And you see that it is not a function of ke. In fact, it will cancel out. It is not a function of ke. So that relationship. So what I'm trying to say is that even if you have an observer, even if you match them with your dynamics and your feedback controller k, you'll see if you look at the response of x hat regarding r, it will not be a function of k, e of the observer. It will only be a function of k. Therefore, the selection of ke does not appear in the response dynamics of the system. So that basically tells you that you can design them separately. They will not affect each other. I mean, the design itself will not affect each other. Of course, the dynamics will be affected, as I explained over here. But, you know, you might have the question, what if I calculate k in a certain way and then I do an observer? Should I change this k based on my selection of ke? The answer is no. They are differently calculated, and whatever I explained in terms of faster, slower, and everything, that's what it is. They don't affect each other in the design. Okay? I mean, this is just another way of looking at it. I just wanted you to have this in your notes. You might want to think about this a little bit, what I did over here. It's not very fundamental. I think we talked about all these things already in the last 2 hours. Okay? So, next week, midterm at this hour. I mean, at 9:40. Okay? And this part is included. Okay? This part is included. Everything is included, up to now. Everything.
The next one is Wednesday, this Wednesday.
This Wednesday, no. Nothing on Wednesday. We will have a class on Wednesday that is not included in the midterm. All right?